These notes are for AP Calculus AB. This is objective 8.6 on integrating the function e to the u. So I wrote down a few things here from our last objective that you'll need to remember. The natural log of e to a power reduces to that power, since the natural log and e are inverse functions of one another, so they undo one another. With that, the last thing that I want to give you here before we get started is this formula. So the integral of e to the u. So the u comes from our substitution. And so we start with the integral e to the u du is just e to the u plus c. So a very straightforward formula. And if you're keeping track, that should be our 8th formula of the unit out of the 10. So with that, we're going to start in on some examples here. All right. So you'll keep looking for this pattern to see if you're just integrating e to the u itself. Right here we have e to some exponent. So anytime it's more than just x, we'll likely want to use our u substitution here. So we have x cubed over 2. We'll start with our substitution there. The derivative there. So we'll get 3x squared over 2 multiplied by dx. So looking to see what matches up with our leftovers, we've got the x squared and dx, just not the 3/2. So we'll divide 3/2 over. We get 2/3 du to replace x squared and dx here. So that now matches what we have. So we remove these two terms, and in their place we have 2/3 du. And inside of our integral, we still have our base e to the power u, since this is our u substitution here. So we get that e to the u. So now to finish off the integral here. So we're going to keep our 2/3 coefficient. Integrating e to the u, we get e to the power u plus c. We'll substitute x cubed over 2 back in for u. And that's our answer. All right, problem number 2. We're going to throw in a definite integral. So 0 to root 2. X times e to the power negative x squared over 2 dx. So like last time, you'll notice you've just got this polynomial piece, e to a power. So that exponent there, its derivative should contain that leftover piece on the outside. So we'll do the same thing here. We'll let u equal negative x squared over 2. Our derivative, negative 2x over 2, will just reduce to negative x dx. So we have the x dx, just not the negative. So we'll divide that negative over. Negative du will go in and replace x dx. So a negative coefficient, du here. My integral is e to the u. We remember, though, that our u values also change. So we're going to make that substitution here. So root 2 and 0 are x values. And I want to do u, integral with u. So I need to find the u values here by substituting those in to this equation. So when x is root 2, we get root 2 squared is 2 negative 2 divided by 2 is negative 1. And if we plug in 0, we end up with 0. So notice, if I want to reverse these numbers, I can make my integral positive. So I'm going to go ahead and do that. We'll make this a positive integral negative 1 to 0 of e to the u du. Okay. With a definite integral, we won't have to go back to our x's. We're just going to keep going and evaluate here with our u values. So integrating e to the u is e to the u. Since it's a definite integral, we don't need plus c. We just want to finish by evaluating from negative 1 to 0. So e to the power 0 minus e to the power negative 1. So any number raised to the power 0 is 1. And e to the power negative 1 is 1 over e. So we can leave our answer like this. All right, so these problems just repeat themselves over and over. Using this integral, you're substituting for whatever the exponent is. Your substitution should give you the leftovers here, and you'll finish as either an indefinite or a definite integral. Okay, so I have a few other types of problems, such as this one here. So fraction with e values. Now, there's more than one term in the denominator, so unfortunately, if there were only one term, we could split it up. But it's not a polynomial, so I can't do long division either. So my only other option is u substitution. So you'll remember those tricks with fractions. Your u substitution is going to be for the denominator piece. So we'll let u equal e to the x plus e to the power negative x. The derivative of e to the x, so you'll remember from our previous objective, is e to the x. The derivative of e to the negative x is e to the negative x times the derivative of negative x, which is negative 1. And then we would multiply over by dx. So you'll notice e to the x minus e to the negative x matches exactly what I have left over here in the numerator and the dx. So this is all taken care of by du. So I replace my numerator and the dx with du. We want to be real careful here. So there's just a 1 now in the numerator. My denominator is the u value. And so my integral is just 1 over u. Integrating 1 over u, anytime that denominator has a power of 1, it's going to integrate back to the natural log of the absolute value of u plus c. So that's all the way back on, I believe, objective 3, where we did this one. Now, substituting back in for u is e to the x plus e to the negative x. And I need to know, do I drop or keep the absolute value symbols? So e to the x, so I graphed it up here. Notice no matter what number you plug in for x, e to the x is always a positive. It's always above the x-axis. So that's always positive, but we're adding to it e to the negative x. So if this were e to the negative 1, it becomes 1 over e. E to the power negative 2 is 1 divided by e squared. So those are just all these small values here, still always positive. And then we're adding those two positives together. So when I substitute this back in, I will not need the absolute value symbols. Okay. So real quick, one more time there, e to the x is just exponential growth, always positive. E to the negative x is exponential decay. but it is still always positive. Okay, so it's just a growth and decay graph. Adding them together, going to stay positive, and we won't need those absolute value symbols. All right, so that's number 3. So number 4 is another fraction problem. This time you'll notice that there's only one term in the denominator. When this happens, we can split up our fraction into 3 individual fractions, simplify each one, and then integrate each one individually. So I'm going to start by rewriting it. We'll have e to the 2x over e to the x. 2e to the power x over e to the power x, and 1 over e to the power x. So in reducing, this is the same thing as anything else with algebra properties. When you have the same base, e, you keep the base and subtract the exponents. So we're still within our integral. E is our base. We take 2x and subtract 1x to get 1x. The second term, the e to the x is reduced. We're left with 2. And the last term, we're going to bring it up to the numerator, just like we would with anything else, and write it as e to the power negative x. So integrate 3 terms individually. Well, integrating e to the x, so this is our new formula, is just e to the x. Integrating 2 with respect to x is 2x. Integrating e to the negative x, so you might use u substitution and let u equal negative x, but that's hardly anything. So I'm going to skip the substitution and not have to use it, but I'm going to be really careful here. Just like integrating e to the x, you should get itself, so you should get an e to the negative x. But let's think about the other way around. If I were taking the derivative of e to the negative x should give me e to the negative x times a negative 1. Well, since there is no negative in front, there must be a negative here. So what's happening when you integrate as opposed to taking the derivative? When you take that derivative, you multiply by a negative. When you integrate, you divide. So dividing by negative 1 is the same thing as multiplying by negative 1, and it's going to give you that negative. Okay? So we saw up here the derivative of e to the negative x is negative e to the negative x, and now you see the integral of e to the negative x is also negative e to the negative x. To finish this problem, we're going to add c, and we might leave it this way, but negative exponents should typically be rewritten. Although if you run into a problem on an FRQ on the AP exam, feel free to leave the negative exponent as part of your final answer. Okay? So I do have a few more examples. I mentioned several times now that you should never have to integrate a natural log. Okay, so we shouldn't have this in here. If you have a natural log in the problem, that's typically your u substitution, but that's only the case if you have a natural log of x. When you have the natural log of e, what you really have is this property. The natural log of e to any power reduces to that power. So this is rather like a trick integral here. The natural log of e to any power is just the power. So we just need to simplify this first. to 2x minus 1. Okay, so remember, natural log and e are inverse operations. They cancel each other out. That brings my exponent here. And then we just integrate it. All right, number 6. So a little bit of a review from Unit 7 using these new functions. So we want area between e to the x, y equals 0, your x-axis, x equals 1, and x equals 4. So I'm going to start by drawing e to the x this way. Y equals 0 is our x-axis. X equals 1. And x equals 4. So it's going to give us this region here, bound between 1, 4, the graph, and the x-axis. We're just looking for area here. So I'm going to draw in my vertical rectangle. I'm going to leave things all in terms of x. So the top here is touching e to the x, the bottom y equals 0. And in finding area, we just do our integral of the height of the rectangle, the width dx. So the height of the rectangle, e to the x minus 0 is just e to the x. The width is dx from 1 to 4. That's the width of our interval, 1 to 4. So that's our setup. We're going to now evaluate it. So integrating e to the x is e to the power x, and then we need to evaluate from 1 to 4. So we get e to the power of 4 minus e to the power 1. And just like x to the 4th minus x can't reduce e to the 4th minus e without a calculator, you're not going to simplify this. You could factor out an e, but there's no reason to. So we'll leave this as our answer. All right. We have one more problem that we're going to work on in this objective. So number 7, and this is again a review. Solving differential equations. So we first worked on solving differential equations in Unit 5. So you might look there to review some of this. This is going to be a problem involving E. So this is a differential equation, differential derivative, okay, derivative equation. So what is it asking you for if it says solve? It's asking you to solve for what y equals. Because we don't have any additional information about the problem, we're finding right now a general solution. If they gave us more information about the original function, like y passes through this coordinate pair, then you're finding something called the particular solution. So we'll see that when we integrate to get from the derivative back to y, we want to integrate. We end up with that plus c general solution, you'll keep the plus c. If it's a particular solution, you'll solve for c. So you want to start by separating your variables. That's always step one. So you'd want to multiply dx over here to the right, and then we could show our integration. Now, the right side is not ready to integrate just yet. So we need to figure out what should we do, because it's this quantity squared. So I don't really have any way of integrating just the outside. I have to also take into account the inside. So what I need to do is, just like a polynomial, if this said x plus 5 quantity squared, you would multiply it out first. So we're going to do the same thing here with the e-values. So e to the x times itself is e to the power 2x. If I multiply e to the negative x with e to the x, so we keep the bases, add the exponents. X minus x is 0. And so we end up with e to the power 0, which is 1. But we do that twice. And then the last term times itself is positive e to the negative x times e to the negative x. So keep that base, add the exponents. Negative x plus negative x is negative 2x. All right. So if that needs a little more explanation, so squaring means we have 2 of them, and then multiplying 2 binomials together, you're just FOILing it out. So multiplying the first terms together, multiplying the outside terms together, keep the base, add the exponents. X minus x is 0, e to the power 0 reduces to 1. The inside terms, exactly the same as the outside terms, so that's where we get another negative 1 from. And then the last term times itself, positive e to the power negative 2x. Again, you're just adding those exponents together. So I would simplify this to a negative 2. And then it's just about ready to go to integrate. And you want to remember, on the left side, you're not integrating dy. We want to think of it as integrating 1 with respect to y. Integrating 1 with respect to y will give us y. Okay. On the right side here, if you want to be able to do this quickly without having to use u substitution here and here, okay, we need to remember how to integrate e to the u. So e to the u is just e to the u plus c. Well, that's if it's just u, if you use your u substitution. So if I want to skip using the u substitution, then I want to remember what I did here. Okay, we kept what we started with, and then we looked at the derivative of our exponent, which was negative 1, and we divided by it. When you integrate, you want to divide by it. So I want to do the same thing here, so I don't have to use the u substitution twice. So I want to keep e to the 2x. The derivative of 2x is 2. And because I'm integrating, I want to divide out that 2. Okay, we're going to do integral of negative 2 with respect to x, negative 2x. And then over here, we want to integrate e to the negative 2x. So we're going to keep it, e to the power negative 2x. And then the derivative of negative 2x is negative 2. Because I'm integrating, I want to divide by negative 2. So negative 2. At the end, we want to add c. Okay. Again, if this were a free response question on the AP exam, I would just leave this as my answer, unless, of course, you were given more information and needed to solve for the value of c. That is very likely. In this case, we're just going to make sure everything's simplified and rewrite our negative exponent. If you prefer divide by 2, you can leave it. If you like writing a coefficient of 1/2, you can write it that way. All right. All right, and that is the end of our notes for 8.6.